So we're looking at section 10.2. We're going to be focusing on graphing square root functions. So although we've seen how to use imaginary numbers to evaluate square roots of negative numbers, graphing complex numbers and complex valued functions is beyond the scope of this course. For purposes of graphing functions based on the square roots, and in most cases where a square root function is used in a real-world example, the domain and range should both be limited to real numbers. So we're going to be limiting our domain and our range. The square root function is the inverse of a quadratic function with a domain limited to positive real numbers. The quadratic function must be a one-to-one function in order to have an inverse, so the domain is limited to one side of the vertex. The square root function is also a one-to-one function, as all inverse functions are. So first thing we have to do is restrict our domain. So the domain of the square root function, we want it to limit to positive real numbers, so we have to make sure that x is greater than or equal to 0. So filling in the table for values of x, we take the square root. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, and we can graph those on our graph. So 0, 0, 1, 1, 4, 2, and 9, 3. So this is going to be our parent square root graph. Looks something like this. So recall that this function is the inverse of the parent quadratic with a domain that's limited to non-negative real numbers. So that means the range of this function will also have to be greater than or equal to 0. The graph appears to be getting flatter as x increases, indicating that the rate of change decreases as x increases. So the slope is getting smaller when our x's get bigger. So describing the end behavior of the square root function, we have to think about it backwards because it's an inverse. So we look as the y's are going to infinity because the y's are going up. The x's are also going to infinity because they're going to the right. So why does the end behavior of the square root function only need to be described at one end? We're only dealing with positive solutions. We've restricted our domain, so we're only dealing with one half of the graph. The solution to the equation x squared equals 4 is sometimes written as x equals plus or minus 2. Explain why the inverse of f of x equals x squared cannot similarly be written as g of x equals plus or minus square root of x in order to use all reals as the domain. The key thing is that inverse functions can't have two y values for a given x, so we can't write it that way. Inverse functions cannot have two y values for a given x value. So we've learned how to transform the graphs of functions using reflections, vertical stretches and compressions, and translations. We're going to apply these same types of transformations to the graph of the square root function. So remember, we don't deal with the horizontal compressions, stretches or compressions. We only deal with the vertical. So any type of square root function is going to look something like this function g of x. We're going to have a on the outside. If it's negative, that's telling us we're going to have a reflection across the x-axis. If it's bigger than 1, it's going to be a stretch, and if it's a fraction, it's going to be a compression. And then inside the function, that minus h is going to tell us which direction we're moving, left or right. And then the k on the outside tells us where we're shifting up or down. So if we've got x minus 2 under the square root, it's going to be a shift or a translation, and it's going to go to the right. The x functions always work opposite of what we think. So then x plus 2 is going to be a shift to the left, 2 units. You can check your answers using a graphing calculator. So here we've got square root of x plus 2. That's going to be another shift or a translation. This time we're going up. And minus 2 outside the square root is going to be a shift going down 2 units. So here we're multiplying by 2. So we've got 2 square root of x. That's a vertical stretch. The key here is the stretch because it's a number bigger than 1 by a factor of 2. And if we have 1/2 times square root of x, that's another vertical. This time it's a compression because it's a fraction by 1/2. Multiplying by negative 1/2 x gives us a vertical compression because of the 1/2, as well as a reflection, that's what that negative means, across the x-axis. It's the x-axis because the y values are what's changing sign. And then -2 times square root of x, the graph is a vertical stretch because 2 is bigger than 1 by a factor of 2, as well as a reflection. That's again from the negative across the x-axis. So our graphs, our equations are always going to look something like this. So when we want to graph these square root functions, we're going to use a couple reference points. So when graphing, it's useful to consider the transformation on 2 reference points, 0, 0, and 1, 1 that lie on the parent function. So the transformed reference points can be found by recognizing that the initial point of the graph is translated from 0, 0 to hk. So the original starting point is telling you where you're shifting left, right, up, down. When g of x involves the parameters a, h, and k, the second transformed reference point is 1 unit to the right of hk and a units up or down. So we know we're going to be moving to the right 1 spot. We want to see how we're changing vertically. That's going to tell us what our value of a is. If a is big, if it's positive, if we're going up, that means a is going to be positive. If we're going down, a is going to be negative. So the transformations of the square root functions also affect the domain and range. In order to work with real valued inputs and outputs, the domain of the square root function cannot include the values of x that result in a negative valued expression. So under the square root has to be positive. Negative values of x can be in the domain as long as they result in non-negative values of the expression that's inside the square root. Similarly, the value of the square root function is positive by definition, but multiplying the square root function by a negative number or adding a constant to it changes the range and can result in negative values of the transformed function. So our square root is going to be positive by default, but multiplying or adding a constant can change what our range is. So we want to find the transformed reference points. First thing you want to do is find the domain. So key thing is that square root input cannot be negative. So what's under the square root has to be positive. So we set x minus 3 greater than or equal to 0, which sets x greater than or equal to 3. So that's our domain. Find the range. What you do is you set the square root function greater than or equal to 0. Then you do any multiplying. So in this case, multiply both sides by 2, which doesn't have an effect on the right side. But then you subtract both sides by 2, which you do to both sides. Once you've done this, now this is your y that you started with, your g of x. So that means your g of x or your y has to be greater than or equal to -2. So that is how your range changes. Now looking at the function here, we can see the changes that are happening. We're moving to the right 3. We're moving down 2, and we're going to be stretching by a factor of 2. So when we're thinking about how our coordinates are changing, if they were originally x, y, we're going right 3, so it'd be x plus 3, and then our y values need to be multiplied by 2, and then subtract 2 for that shift there. So applying those changes to the coordinate 0, 0 gets these new coordinates, which they plotted on the graph. Now, notice with this one, there's that -1/2 under the square root. This means there's going to actually be a horizontal stretch, but we don't do these. So we're not going to graph this one, but I do want to go over how to find the domain and range, because that's an important thing. So first thing you need to do is set what's under the square root greater than or equal to 0, because that needs to be positive under the square root. When in the next video, then we'll finish discussing these and finish off with the lesson.